And now for the moment you've been waiting for. We've already gone through the first four models of the atom, actually, all the way back to the original idea of the atom from the ancient Greeks. Up through Model 4, we left off with Bohr's Model 4, which was the first model, and it really ushered in the quantum age where electrons were only allowed to have certain energies. So electrons are allowed to occupy certain energy levels. In other words, they could only have certain quantities of energy. They could only take in so much energy or give off certain amount of energies. But there were the problems with Bohr's model. It did not explain the emission spectra of larger atoms. So there must be more to the electron than traveling in these energy level orbits. There had to be something more. And this is where the fifth model takes over, the model we've been building for, the model which will hopefully answer where these magic numbers of 8 came from in the octet rule, or 2 for the duet rule, or where the number of electrons that each energy level could actually hold, 2, 8, 18, 32, 50, etc., etc. Well, Model 5 came about really from an understanding of the behavior of light and applying that to the behavior of other things. Around the early part of the 20th century, there was a big argument between scientists about what light actually was. And it was the great Einstein that put forth the idea that light was a wave but behaved like a particle. And he used this to explain something called the photoelectric effect, and this brought Einstein great acclaim because he was able to explain something nobody else could explain by assuming that light had to be a particle. The photoelectric effect is really the situation where light can cause electrons to be knocked off atoms and generate an electric current. But only certain frequencies of light worked. And this is where Einstein realized that light had to behave like a particle in the first place in order to knock electrons off atoms. And the photoelectric effect is used today in solar cells, because when light energy hits solar cells, it causes an electric current. But Einstein's explanation of it was huge. Light was a wave that had the dual nature of being a particle. If that's the case, if light can interact with electrons, which are particles, could the electron be a particle that behaved like a wave? In other words, light is a wave that behaves like a particle. Could the electron be a particle that behaved like a wave? And this was proposed by de Broglie. However you would say it. De Broglie is how I say it. And this was right around the middle part of the 1920s into the latter part of the 1920s, 1925 to 1927. Electrons are particles that behave like a wave. If that's the case, then the mathematics that goes along with waves, calculating wave-like motion, could be applied to the electron, perhaps, to better explain the behavior of electron and maybe fill in the missing gaps of this two-dimensional orbit. You see, when something travels or behaves like it's a wave, it's actually moving three-dimensionally, up and down, side to side, back and forth. It's moving all directions, side to side, back and forth, up and down. Where the orbits were two-dimensional, if an electron behaved like a wave, it would be three-dimensional. So Schrödinger began to apply the mathematical equations that relate to wave motion. And he did this with the intent of really trying to unlock the secret of the probabilities of electrons being in certain three-dimensional spaces surrounding the nucleus. Schrödinger, following the Heisenberg uncertainty principle, which says you cannot simultaneously know the momentum and position of an electron, Schrödinger realized that it was more calculating probabilities of where an electron might be found, the likelihood of it being found in a certain position by using the wave equations. And this led to the quantum mechanical model of the atom. Quantum meaning numbers, mechanical meaning equations. Schrodinger wanted to put numbers using the wave equations to the likelihood of finding the electron in certain places, knowing that the electron was traveling with a three-dimensional motion. In other words, if the electrons were going up and down, side to side, back and forth, the electrons weren't nice little orbits like this, two-dimensional, but rather they were three-dimensional orbits creating a space around the atom. So when we look at Schrodinger's model, the nucleus is in the center, but the three-dimensional motion of the electron gave rise to a cloud, where the darker parts of the cloud would be places where there was a higher probability of finding the electron. As they were working with the equations, obviously we're no longer considering two-dimensional orbits by Bohr. Bohr was able to show that the emission line spectrums that Bohr couldn't explain could better be explained by treating the electron as having three-dimensional wave-like motion. This three-dimensional wave-like motion, they need another term. Rather than orbit, they went to orbital. Orbitals are three-dimensional spaces surrounding the nucleus where there was a probability of finding the electron at the highest. So orbitals are three-dimensional, orbits were two-dimensional. And now we're embarking upon the basic ideas behind Schrodinger's quantum mechanical model. Quantum again meaning numbers, mechanical meaning numbers that came from the wave equations. Schrodinger maintained, as did Bohr, that electrons were only allowed to have quantized energies, which means they could only have certain allowable energies, and quantized means they could be expressed in terms of quantum numbers. Schrodinger's work led to the realization that quantum numbers would be needed to explain where the high probabilities of finding electrons were. What are quantum numbers? They are a set of integers, in other words, numbers, whole numbers. Or in the case of one of the quantum numbers, a half integer, plus half or minus half for one of the numbers. And it characterized the probabilities and energy states of the electron in the atom. The electrons in the atom were actually held in the atom by electrostatic attraction between the positive nucleus, the nucleus had protons in it, and the negatively charged electrons. That attraction between the negative electrons and the positive protons is called an electrostatic attraction. Opposite charges attract. He realized that the electron waves were standing matter waves. In other words, matter does behave like a wave. Standing matter waves have quantized energy. That means they're represented with quantum numbers. And these standing matter waves are three-dimensional. When they say talking about standing matter waves, it's like you have a rope and you're holding both ends of the rope and you're snapping the rope, causing the rope to go up and down in the middle. If you start snapping it faster, it'll go up and down in different places and it might actually stop moving in the middle. So the more you snap the rope up and down, the more places you're going to get motion. In other words, the higher energy that you're snapping the rope up and down, the more places that that rope is going to be moving. So Schrodinger's picturing the electron as being like on a rope that's being snapped up and down, causing the electron to move up and down, or snap side to side, causing the electron to move side to side as it's moving back and forth. Bohr, on the other hand, kind of pictured the electron on a wire. In other words, just going around and around in a circle, a circular wire surrounding the nucleus. Now, it wasn't actually on the wire, but that we know the electron's not on wires, but it just was behaving like it was on a wire. It was moving along that one-dimensional orbital path. When you only have that one dimension to your motion in that flat plane, you only needed one number to describe it. So Bohr's model had the E1, E2, E3 for the energy levels, or N1, 2, 3, 4, 5, 6, 7, or KLMN, OPQ. You only needed one number on Bohr's model. A three-dimensional model where it's going up and down, side to side, and back and forth, you would need three numbers. And you would need a fourth number because they realized the electron was actually spinning. So the quantum mechanic model required 4 numbers because there's 3 dimensions and a spin to the electron. So the electron was actually spinning as it's going up and down, side to side, and back and forth. A 3-dimensional standing matter wave describes the state of an electron. That's called an orbital. Orbitals, once again, are 3-dimensional. Bohr's orbit was just 2-dimensional. The energies and mathematical forms of the orbitals could be computed using Schrodinger's equation. So Schrodinger developed equations that will lead to the energies that the orbitals could have. And in Schrodinger's model, the quantization is not assumed. Those quantities that the electron could have high probabilities of having are an outcome or a solution. Every electron, we had those 3 variables, the x, y, z's, that needed to be solved. Those were very hard equations, lots of variables, hard equation to solve. But what was found in these solutions, Schrodinger's equations led to the explanation of the bright line spectrum bands from all atoms, not just hydrogen. So the quantum mechanical model by Schrodinger solved the problems of Bohr's model. So what did we learn in this video? That there are 4 quantum numbers that are necessary to fully explain the orbitals, the 3-dimensional spaces where there's high probabilities of finding electrons. In our next video, we're going to begin taking a closer look at those quantum numbers.